All right, welcome. Here you have the AP Physics multiple choice solutions for conservation of energy. Here we have, let's see, 24. Oh, I actually did 24. If you look at the previous question video, I went over it. The answer was B. Okay. Let's start on 25 here. A 5 kilogram mass undergoes a change of momentum of 10 kilograms during a 4-second period of time. What is its impulse? So a couple of things for the impulse. That the formula wise for the impulse, you could write impulse is equal to your mass times your change in velocity. Sometimes your impulse here you're going to see as a delta p, right? So we know that the mass is 5, and we know that the change, what, this is the what, a change in momentum is 10 kilograms meters per second. Oh, you already have it. That's the answer. They already say it. Yeah. What is the impulse? The impulse, by definition. So this is a definition question, okay? So the impulse, by definition, is equal to the change in momentum. Okay? That's it. There's nothing different about that. 26. A 2 kilogram ball goes 10 meters per second, follows a path that is perpendicular to a surface, impacts a wall, losing 20% of its momentum in collision. What is the magnitude of the impulse of the wall? All right, let's take a look at this here. Okay. So the formula you want to take a look here is that the impulse, so I'm just going to use the right notation, P is going to be equal to M times delta V. Okay, this just stands for impulse, okay? All right. This stands for change of momentum because, okay. All right. Okay. Side note, if you don't understand, P is your momentum. Okay. So it's not a P, it's like a weird P like this, okay? Alright, so this is impulse, the change in momentum is equal to mass times the change in velocity. Okay? And we know that this is equal to the change in velocity is velocity final minus velocity initial. Okay? And here we have the mass is going to be what? 2 kilograms. Okay? Mass is equal to 2 kilograms. Then you have your velocity final. Let's say it's 10, so let's say it's 10. So velocity final was what? Loses 20%. So loses 20% is basically 0.80, okay, of 10. And then you have velocity initial as just your 10. Okay, so this becomes, hold on. Okay. Okay, and we know that the initial and the final velocity, okay, had there was a loss of 0.8 times your 10, and this is going to be minus your initial, which is your 10. Let me explain this, okay? This is your lose 20%, okay? And this, all right, this is your lose 20% of your 10. Okay, that should explain it. Okay, lose of your total is 1, correct? Okay, and then we know that it's a 1 minus r if it's a loss, and it's a 1 plus r if it's a gain. Okay, we just have to remember that. Okay, here it's losing 20%, so it's what? Minus 0.80. It's 80%. Okay, All right. So why is it negative? It's being a loss. Okay. All right. That's also the final velocity. Okay. So you plug it in. Get here. You get negative 8. This should be negative 8. Yep. Times negative 10. This gets you your negative 18. Gets you negative 36. But here it says magnitude. So here, you're taking the magnitude of that, just becomes 36 kilograms per meter second squared. Should be D. The hard part is understanding that it's the loss of 20%. Okay, make sure you're using a negative 0.80. Here, next, 27. What would be the speed of a 3 kilogram pass? Or realistically traveling 2 meters per second that undergoes the motion graph above. What would be the speed? All right, so let's take a look here. Okay. So in the graph, you want to look for your intercept, slopes in your area. Okay. Slope and the area are the biggest in this class. So slope is the rise over 1 or force divided by time. Okay. So here, the slope is equal to the force divided by the time. Okay. This does seem like anything. Area is the base times the height, but formulas are always in the height times base order. So try force times time, and we get the impulse formula. Okay, so let's take a look here. We have delta P is equal to mv minus v naught. Okay, oops. I don't like this version, so I write F minus v initial. Okay, again, this just stands for your impulse. Okay, all right. Oh, so velocity. So a couple of things we can change from: force times time. Force times time. Okay. So, so here, this, trying to find the area here. Oh, that's horrible. I can just feel the area here is 6. How do I get that? Okay, so how can I see it? How do I do 1/2 base times height here? It's 3 times. Okay, look. Like length is equals to 3. Width is 4. So the area of a triangle is 1/2. I do length times. Sorry, base height is base times height. It's 1/2 times 3 times 4, which is equal to what? 6. That's how I get the area of 6. Okay? Alright, so I have my change in momentum, okay, which is my impulse, okay, which is going to be equal to 6. Okay. What would be the speed? So I'm looking at, I believe, v final. That's my question mark. So let's just redo this. So here, distribute mass times velocity minus mass times velocity. Mass times velocity final minus mass times velocity initial. Impulse. So add that. Mass VF. Okay, so divide this by M. That's what I got. Alright, so I have what mass initial. Oh, let me split this impulse here. This is mass over mass VI. These cancel out. Comes VF. So let's plug it in now. Your impulse was your 6. Your mass was your 3. Plus 3 over 3 is just 1. V initially going at 2. That gets you your VF. 6 divided by 3 is 2. 2 plus 2 is just 4. So there you go. Right? A couple of things that you would be like asking how to approach this is that you're looking for VF and that this is your force and time. Okay? You would have to find the area here, okay? Because some of you right here are not understanding that V or delta P is equal to also your force times your time. Okay? This is your right. That's how I got the area here. So you could also say this is equal to your area of the force and time graph. All right. Looks 28. Two objects have the same momentum. How can one of the objects have more energy? Okay. If they have the same momentum, they have mv and mv. They have the same momentum. How can one object have more energy? Well, this is mass velocity squared, and this is 1/2 mv squared. Alright, so if you take a look here, is that the energy has a square component. Okay, so we're going to see how that affects it. Alright, so the two objects here, if there are two objects and one goes faster, it has to have less mass. Okay, so if two objects have the same momentum, how can one object have more energy? Okay, so this means more energy means more velocity. Okay, so check this out. This means the mass here has to be lower. The mass here has to be smaller, and the velocity has to be greater for these to be the same. Okay, like this. Let me give you an example. Okay, let's say the velocity here is 10 and the mass here is 10. Okay, you would say that this is 100, but here let's say this goes twice as fast, right? 20, right? So this has to be 5. Do you see how the mass is less here? So the mass is less, is halved here, right? Okay, so here if mass is indirectly proportion, right? Okay, so the velocity squared is what happens, okay? So if there are two objects, the one going faster has to have less mass in order to have the same momentum. I just showed that right here, okay? But when it comes to energy, okay, notice that the velocity is squared. So the object with more speed will have higher kinetic energy without having more momentum. So you can say that an object can have higher kinetic energy with having more momentum. Okay, right here, the object here can have higher momentum, can have the same momentum, but here it has a higher kinetic energy. Okay, so an object with more speed has a higher kinetic energy without having more momentum. 29. All right. When no force is acting, momentum is conservative and so what is a elastic collision? Elastic collision is like when a ball hits another ball and it becomes ball and a ball moving. Okay. Inelastic is like a ball hits a ball, and it's a ball and a ball, and they move together. Okay. Explosion is more like a opposite, like here, right? It explodes equals to an object moves this way, and then an object moves this way. So this is elastic, inelastic, explosion. They're all true. Momentum is conservative. Okay. Here, let me label it for you if you want to see it. This is an inelastic collision. This is a inelastic collision. And the fact that a mass breaks is considered an explosion. Right? Okay, let's take, I think 30 is up here. Alright. A 2 kilogram ball is moving at 3 meters per second, collides with a 4 kilogram object that is stationary. If the collision is perfectly inelastic, what is the speed of the 2 kilogram ball after the collision? Alright, so let's take a look at how we're gonna set this one up. Okay. Alright, so we have the 2 kilogram block, a 2 kilogram ball, so mass is 2 kilogram, and velocity here is 3 meters per second. It hits a, let's see, green ball. The mass here is kilogram, oh, 4 kilogram, and V equals to 0. Okay, and what happens here? It's perfectly inelastic. Okay. So perfectly inelastic means it connects. So let's take a look. And then it hits together. Then it becomes the red ball, and the mass ball is going to be together. Because again, this is perfectly inelastic. Alright, so here, momentum V plus this momentum V, oops, is equal to this momentum, which is the masses together, times velocity. But notice this goes to 0. Okay. So, what is the speed of the 2 kilogram ball after the collision? Okay. I'll just solve for this. mv divided by m1 plus m2 is equal to v. Okay. Remember, they have the same velocity. They share the speed of the 2 kilogram block is together with this. They share the same velocity because they're together. Okay. So plug it in. 2 times 3 is over what? 2 plus 4 is the v. So that's 6 over 6 velocity. So velocity is just 1 meter per second. It's right here. Right. It's positive. A fifth, here using this information, a 500 kilogram rocket is at rest. The rocket burns fuel at 10 kilograms of exhausted, blah, blah, blah. This process takes 10 seconds. 31. Okay. What is the total momentum in this system? Alright. So, what is the total momentum in this system? Let's see. What is the total momentum? I know the momentum issue. Hmm. Let's see. Okay. Let me take a look here. So we have the rocket, alright? And the rocket is at rest. So the is mass is 500 kilograms, and it's at rest. At rest. Does that mean A equals to 0? A that's equal to 0. Well, that's question mark. If you use question mark though, not sure. The rocket burns fuel, pushing 10 kilograms of exhausted gas air at 400 meters per second. So then this becomes the rocket, and the rocket is what? 4990 kilograms, because here it's the what? This is the gas, and the gas was 10 kilograms, and here it has a velocity of 4,000 meters per second. Okay. What is the total momentum? That is very interesting. Okay, hold on. Let me think about this. Okay, let me think about this. Hold on. Okay, so what's happening here when the rocket is burning? This is considered a an explosion. Okay, and in the process of the explosion, so the equation is basically correct. It's still mv. It's still going to be equal to mv, but this is the mass of the rocket, and this is the velocity of the rocket. This is going to be the mass and the velocity of the exhausted gas. Okay, so we were setting it up correctly. Okay, here you didn't know what this is, so you're probably going to just look at this. Okay, this was what, 400 kilograms, 4,000 meters per second was the velocity, and it was 10 kilograms, so that would become 40,000. Okay, which is C, because we don't quite know what this is, but we know that momentum has to be conservative. So if this is 40,000, this also has to be 40,000. Okay. Next, what is the force that is being applied to the rocket? Okay. This is another formula. This is just looking at total momentum. Here, the force one, you want to look at your momentum is equal to force times your delta t. Right, we saw that earlier. And okay, a couple of things is here you can actually have the changed the momentum here can also be changed to this. Vf minus Vi is equal to force times delta t. Here you want to solve for the force, so the force is equal to, let's just divide that, mass times velocity, time, okay, or F is equal to ma, right? What is A? A is what? Velocity final minus velocity initial divided by t, okay? This is deriving it, or you could derive it from this way. Okay, there's two ways to derive this. This is using momentum. Okay, this is just using your force equations. Force. So what is the mass? 5,000 times. What's my velocity? Final was what? Oh man, 40,000. 5 my time is 10 seconds. That got me 4,000. Right? Is that right? Hold on. The mass is, my velocity is 5 0. Divided that by the initial times that. 1, 2. Hold on. Give me a second here. I'm taking a look at the answer. My work here. Hold on. I should be right. The rocket burns, blah blah blah. Total. Okay, hold on. Let's see. Um, what is the total force? Average force, right? Mm-hmm. Yeah, that is right. That is right. Process. So it's 5,000 divided by 10, and and it takes what 10 kilograms meter. Yeah, takes 10 seconds. The kilogram. What is the average force that is being applied on the rocket? Okay. So its mass, which is just what 5,000 times the the final velocity, which is what 4,000 meters per second squared divided by 10, but we would be off. What is the average force? 10 kilograms exhausted reward process takes 10 seconds. Well, I have to divide by 10. The rocket burns 10 kilograms of exhausted air reward at 4,000. Hold on, I'm going to pause this and I'm going to do some more work. Hold on. Alright, check this out. Oh man, okay. I was looking at it. So if I go back here, I saw that my new velocity is equal to the original mass times its velocity divided by my new mass. Alright, so this becomes, my new velocity becomes 4,000 divided by my 5,000 times my 10. Okay, this should get me my velocity equals to 8. So here, the mass is the mass becomes, hold on, the mass becomes 5,000. V initial is just V final is 8. V initial is 0. Time is just 10. This should get you 4,000 newtons. Okay. This is the new velocity. But here's the interesting part about this question. It's total momentum. Total momentum. What is the total momentum here? 4,000 initial and 4,000 final. This is interesting. You could make the argument for it to be 0 kilograms. So this would be the change in momentum, right? The change in momentum is 0, but this is the momentum produced by the exhausted air. Okay, that's interesting. Determine the rocket speed. We actually did that. It was right here. Okay. Um, I could work through this deviation a little bit for you if you want to see it, because it explains how I got the 8 here. Okay, so we have mv is equal to mv1 times. So let me explain how I got this. So this is rocket. Okay, this is going to be the rocket plus the air. That's basically what happened. Okay, the rocket wasn't moving. That's 0. So it just becomes rocket plus the air. Okay, so this becomes 5,000 times your v. Okay, plus your mass was your 10, and your velocity here was 4,000. 2, 3. So, all right, that's your your rocket for your velocity. Okay, so divide things over. So we divide this over. Let's do some math here. Uh, 1, 2, 3 equals 5,000. V should be equal to 8 once you divide it. Okay, so this I should have done that. I should have done 33 first before 32. Yeah, that would make more sense. Here gives you the explanation for why that is true. Okay. How do I get mv rocket is equal to mv exhaust? Just comes here from the conservation of momentum. Okay. All right. 34. Uh, a large rocket. No, sorry. This is a large mass explodes into two small mass. Mass m moves to the right. V mass m moves to the left at v. Calculate the speed. Okay. So that's a very easy one to do. Okay. So we know that the mass explode m1 moves, so you have a bigger mass here. So originally you had the small mass with the big mass times its velocity, right? This is before the explosion. Now it explodes, so it's just the mass times its velocity plus the other mass with its also its velocity. Okay, so we know that it was at rest, right? Yeah, can we assume it's at rest? Yeah, because it's an explosion, so this is gonna be at 0 because this is an explosion. So all you need to do is your small mass times its velocity is gonna be equal to its one of them is gonna be big, one of them is gonna be small. So one of them is gonna be a minus anyways. Okay, so solve for its velocity. These are all magnitudes anyways. So solve for its velocity, divide. So what? It's mv divided by m is equal to b final. Just take the magnitude of this. Okay. So it is this one. Okay. And what is my explanation for why? Um, Remember that technically one mass needs to have a greater negative momentum, but it's asking for speed, right? So it's asking for speed, okay? Speed is the magnitude of velocity. Velocity. There you go. All right. That's why I'm allowed to take the magnitude here. 35. Up. This image was supposed to be for the next question. All right. The next one. Same process, but here that you don't know it. So here, you see, I'm just gonna grab this. It's so much easier to take a look at. So do you see this? I'm just gonna grab the answer here. It's the same. It's almost the same scenario. Right? It's almost the same scenario, but what is the difference? The difference here is that the speed of the remaining piece. You don't know what the remaining piece is. Okay, you don't know of the of the remaining piece, so you don't know. How does that affect this? So the MV stays the same, but now your bigger M gets removed. This is the this um, is the is the remaining piece. Okay. The missing mass is what remains of M. After breaking off, M breaks off. So this is the small piece that breaks out. This is the original. Okay. So it's the same thing here. It's just this gets reduced by the M, which is the small piece that flew away. Okay. And last one. Oh, I hate this question. Determine the total momentum here. Alright, so let's make sure I've been recording. Alright, good. Alright. It's like if you want to see the time, like it's midnight. Okay, it's past midnight and I'm falling asleep. Okay, so bear with me. I just wanted to make sure I get your solutions out. Ah, my head hurts. Okay. So here, this is a triangle at 90 degrees. Here you have a momentum. Here you have a momentum. And it's asking for the total. Alright, so here you would have to bust out Pythagorean theorem, right, for the most part. So the P total is going to be your P in one direction. So this is going to be in your momentum in your X direction, momentum in your Y direction. So that's your P in your X plus your P in your Y. Okay. And we know it's squared. These are all squares, right? Because please understand where I'm getting this. A squared plus B squared equals C squared, basically. Okay, I just reflected. Okay, so momentum is equal to, here is the square root mv squared plus mv squared. All right, this is just 2mv squared. So this becomes a 4mv squared, right? Square root of that, you should already know what the square root of 4 is. It's 2. Wait. That becomes 2. Oh, this is bad. That is correct. Yeah, so this should be a 2. Okay, so that's square root of 2. Right? We know this cancels out. Okay, so this becomes mv. Okay, so what? This becomes, hold on, this becomes square root 2 mv. So something interesting you want to notice that the total momentum, if it's linear, is just mv, right? But once it looks like this, there's a square root of 2, and I think, what is the square root of 2? The square root of 2 is roughly falling asleep here. The square root of 2 is roughly 1.41. So in this case, this has slightly higher than the linear because it's a 1.14 being multiplied into the mass times velocity. Okay. So there you go.
It's not 2 MV. A lot of people think it's 2 MV. That would make sense if it's like both linear, but it's not. When it's in a weird angle, you have to throw in some Pythagorean. Okay, so there you go.